Good day everyone. Welcome to hydrology class. I am Xenita Mirano with Myrell Naguiat, Loryllaine Austria, Dan Palaguyan, Robin Prince Cunanan, and Jonnel Tamayo. We are here today to discuss about evapotranspiration. These are the topics that we will tackle along the discussion. First one is what is evapotranspiration? Evapotranspiration is simply a combination of evaporation and transpiration. Evaporation is a process by which water changes from liquid state to a gaseous state, and transpiration is a specific action of water evaporating from plants. Transpiration is confined to daylight hours, and the rate of transpiration depends upon the growth period of the plant. On the other hand, evaporation continues all through the day and night, although the rates are different. Evapotranspiration is also called consumptive use of water. And mathematically, consumptive use is equals to evapotranspiration, which is equal to evaporation and transpiration. For atmospheric condition, evapotranspiration depends on the availability of water. These are some terms or stages. Field capacity, maximum quantity of water that the soil can retain against the force of gravity. In the field capacity, the soil is wet and contains all the water it can hold. Permanently wilting point. At this stage, the soil still contains some of water, but it is difficult for the roots to extract from the soil. Available water. Difference between moisture available for plant growth and moisture at wilting point. When the soil moisture reaches the permanently wilting point, the evapotranspiration reduces to zero. This picture is an example of soil water status. First is saturation. The plants absorb as much water as it can. Next is gravity water drains, where draining of water starts. Then field capacity, where dripping of water stops, and in this situation, it holds the maximum available of water. Next is readily available water, where the evaporation first takes place, and it also the portion of available of water accessible to plants. As water depleted from soil profile, the remaining water holds tighter to soil particle. Therefore, it is more difficult for the plants to extract from the soil. Then it comes to the point that the plants can no longer extract from the soil, and it is called permanently wilting point.
Tamayo and Naguiat, and I will be discussing measurement of evapotranspiration. Measurement of evapotranspiration is measured by using lysimeters or by the use of field plots. Field plots is a method provides fairly reliable results. In special plots, all the elements of the water budget in a known interval time are measured and the evapotranspiration determined as evapotranspiration equals precipitation plus irrigation input minus runoff minus increase in soil storage minus groundwater loss. Measurements are usually confined in precipitation, irrigation input, surface runoff, and soil moisture. Lysimeter is a measuring device which can be used to measure the amount of actual evapotranspiration which released by plants, usually crops or trees. A lysimeter is a special water tank containing a block of soil and set in a field of growing plants. The plants grow in the lysimeter are the same as in the surrounding field. Lysimeters should be designed to accurately reproduce the soil conditions, moisture content, type, and size of the vegetation of the surrounding area. So we have a picture here. We have a lysimeter apparatus for measuring evapotranspiration. We have a rain gauge, a tank, and a receiver. There are different types of lysimeter. First is the volumetric lysimeter, which means evapotranspiration by volume. Example, drum-type lysimeter used in polycarps. So we have a diagram here shows the volumetric lysimeter system. The second one is floating lysimeter used for aquatic crops. And the third one is gravimetric lysimeter, which means measures evapotranspiration by weight. So we have a diagram here shows this E is for evaporation. It is the change of water from liquid to vapor form. And we have here a T. It is a evaporation from plant leaves through the small openings in the leaves called stomata. And we have here I for the inflow and delta MC for change in moisture content of soil, and O is outflow. By recording the amount of precipitation that an area received and the amount lost through the soil, the amount of water lost by evapotranspiration can be calculated. So together, we have ET equals I minus O minus delta MC, where evapotranspiration equals ET and delta MC equals change in moisture content of soil, I equals inflow, O is outflow.
So, good day everyone. I am here to discuss one of the equation of evapotranspiration, which is the Penman's equation. Penman's equation is based on the sound theoretical reasoning and is obtained by a combination of the energy balance and mass transfer approach. And the formula for Penman's equation is PET is equals to AHN plus EA multiplied by Y over E plus Y, where PET is the daily potential evapotranspiration in millimeter per day, and A is the slope of the saturation vapor pressure. HN is the net radiation in millimeter of evaporable water per day, and for EA, it is the parameter including the wind velocity and saturation deficit. And Y is a psychometric. We have its psychometric constant of 0.49 millimeter of mercury per degree Celsius. And the net radiation is estimated by the following equation. The net radiation, which is the HN, we have its equation, which is HN is equals to HA multiplied by 1 minus R multiplied by A plus B times N over N minus sigma PA raised to 4 times 0.56 minus 0.092 square root of EA times 0.10 plus 0.090 times N over N, where HA is the incident solar radiation outside the atmosphere on horizontal surface expressed in millimeter of evaporable water per day. A is a constant depending upon the latitude and is given by A is equals to 0.29 cosine latitude. And for B, we have a constant value for B, which is 0.52, and N, the small letter N, is the actual duration of bright sunshine in hours. And for the other N, it's the maximum possible hours bright sunshine. And for the R is the reflection coefficient or the albedo. And for the usual ranges of values of R, um, we have the table at the slide. Um, Surface for the closed ground corpse, we have 0.15 to 0.25. And for the bare lands, we have 0.05 to 0.45. And for the water surface, we have 0.05. And for the snow, we have 0.45 to 0.95. And sigma is the Stefan Boltzmann constant is equals to 2.01 times 10 raised to 9. And for the TA is equals to the mean air temperature in degrees Kelvin is equals to 273 plus degrees Celsius. And for the EA is the actual mean vapor pressure in the air in millimeter of mercury. So in the parameter EA, we have the EA. To get the value of EA, we have a formula of EA is equals to 0.35 multiplied by 1 plus U2 over 160 multiplied by EW minus EA, in which U2 is the wind speed at 2 meter above ground in kilometer per day, and EW is the saturation vapor pressure at mean air temperature in millimeter of mercury, and EA is the actual vapor pressure. And for the example, calculate the potential evapotranspiration from an area in the month of November by Penman's formula. So we have the given latitude is equals to 30 degree north, elevation is equals to 220 meter above sea level, mean mountain temperature of 20 degrees Celsius, and mean relative humidity of 75%, mean observed sunshine hours is equals to 9 hours, wind velocity at 2 meter height is equals to 80 kilometers per day, and the nature surface of cover is equals to close ground green.
Empirical formula. It is available for estimation of PET based on climatological data, but not universally applicable to all climate areas, and should be used with caution in areas different from those from which they were derived. The Blaney-Criddle equation. It is based from the data from arid western United States. It is a relatively simplistic method for calculating the evapotranspiration. It is ideal when only air temperature data sets are available. It is recommended to use to calculate the evapotranspiration for a period of 1 month or greater. The potential evaporation of a crop growing is given as E sub t is equal to 2.54 times k multiplied by f, and f is equal to summation of p sub h multiplied by bar t sub f over 100, where E sub t is equals to PET in a crop season in cm, k is the empirical coefficient, m is the sum of the consumptive, p sub h is the percent of the monthly annual daytime R, and bar T sub F is equals to mean temperature in degrees Fahrenheit. The values of K depends on the month and locality. We have here the table that shows the monthly daytime R that we use for the Blaney-Criddle equation. The next table shows the values of K of the selected crops. Example for the Blaney-Criddle equation. Estimate the PET on the area of the season November to February in which wheat is grown. The area is in North India at a latitude of 30 degrees north with a mean monthly temperature of, for November, we have 16.6, December is 13, January is 11, and the temperature for February is 14.5. For the solution, first, look at the table 3.7 to look for the value of K of the wheat, which is 0.65. Second is to look for the table 3.6 to look for the monthly percent of the annual daytime R of November, December, January, and February. The third is to convert all the degrees Celsius of every month to Fahrenheit. Then, use the formula of the summation of P sub h multiplied by bar T sub f over 100 to get the value of 16.26. By using the formula E sub t is equal to 2.54 times k multiplied by f, we will get the value of 26.85 cm.
Good day. My name is Robin Prince and I'm here to report the potential evapotranspiration. What is potential evapotranspiration? Potential evapotranspiration, or PET, is the amount of evapotranspiration or evaporation that may occur if plenty of water is present in soil, a water source, or plants. It is possible to estimate this amount using equations. So here is the sample illustration of how the potential evapotranspiration, or PET, happens. Humans are involved in the production of variety of plant crops. Many of these crops grow in environments that are naturally short of water, so they use irrigation. Irrigation is used to supplement the crop's water needs. Managers of these crops can determine how much supplemental water is needed to achieve maximum productivity by estimating potential and actual evapotranspiration. So sa mga lugar na hindi ganong sagana sa tubig, ginagamitan na nila ito ng irrigation para mas makuha ng halaman yung sustansya na kinakailangan nito. So para makuha kung gaano karaming tubig ang kailangan ng halaman, ay makukuha natin ito sa pamamagitan ng equation na ito. Potential evapotranspiration minus actual evapotranspiration equals to crop water need. So dito, makukuha na natin kung gaano karaming tubig ang kailangan ng mga halaman upang ito ay mabuhay. There are factors that are extremely important in estimating potential evapotranspiration. Una is yung araw. Yung araw is the major source of energy ng mga halaman. Kaya isa ito sa pinaka-importante sa pag-estimate ng potential evapotranspiration. Sunod ay yung hangin. Wind enables water molecules to be removed from the ground surface by process known as eddy diffusion. Pangatlo, rate of evapotranspiration is associated to the gradient of vapor pressure between ground surface and the layer of atmosphere receiving the evaporated water. Thank you.
Everyone, I am Jonnel R. Tamayo and I will discussing actual evapotranspiration. What is actual evapotranspiration? This is the hydrological cycle that the most important process in a natural ecosystem that explain the water and energy between the soil, land, surface, and atmosphere. And also, this is the quantity of water that is actually removed from a surface due to the process of the evaporation and transpiration. Initial loss. In the precipitation reaching the surface of a catchment, the major obstruction is from the infiltration process. However, two other processes, though small in magnitude, operate to reduce the water volume available for runoff, and these act as obstruction. These are the interception process and the depression storage. In interception process plus depression storage is equal to initial loss. This abstraction represents the quantity of storage that must be satisfied before overland runoff begins. The following two sections deals with these two processes briefly.
Interception. What is interception? It is the removal of water that wets and adheres to plant foliage, buildings, and other objects above ground surface. This water is subsequently removed from the surface through evaporation. Interception can be as high as 2 millimeters during a single rainfall event, but typically removes about 0.5 millimeter during a single rainfall or storm event. So sa pagkuha ng interception losses, this is the equation. L sub I is equal to S plus KET, where L sub I is the total volume of water intercepted, and the S is the interception storage. K is the ratio of surface area of the leaves to the area of the entire canopy, and E is the rate of evaporation during the precipitation event, and the small letter t is for the time. Here is the graph of it, sample graph for interception. There are three main components of interception: interception loss, throughfall, and stem flow. The first one is the interception loss. The water that is retained by vegetation surfaces that is later evaporated into the atmosphere is absorbed by the plant. Interception loss prevents water from reaching the ground surface and is regarded as primary water loss. So sa interception loss, kailangan dumalo yung tubig mismo doon sa halaman at hindi na dapat umabot pa doon sa lupa. Kailangan na ma-absorb ito, kung hindi, mag-evaporate na ito or mapupunta sa ground surface at maituturing na water loss. Malaking water loss. The second one is through fall, the water which falls through spaces in the vegetation canopy or which drips from the leaves, twigs, and stems and falls to the ground. Stem flow, the water which trickles along the stems and branches and down the main stem or trunk to the ground surface. So, ito yung tubig na dumadaan mismo dun sa mga main stems and branches hanggang sa ma-absorb nito ng halaman ang tubig. Thank you.
The volume of water trapped in the depression is called depression storage. This amount is eventually lost to runoff through processes of infiltration and evaporation and thus form a part of initial loss. When water temporarily accumulates in a low point with no possibility for escape as runoff, the accumulation is referred to as depression storage. The volume of water in depression storage at any time during a precipitation event can be approximated as Lensley 1982. The formula is V equals S sub D multiplied by 1 minus E minus KPE, where V equals volume of water in depression storage, S sub D equals maximum storage of capacity of depression, P sub E equals rainfall excess, and K equals constant equal to 1 over S sub D.
That's all everyone we wanted to share with you. We hope that you understand and learned a lot about our discussion. Keep safe and God bless you all.